Hi everyone, I'm glad to be talking today about my work Blaze, a data processing system that provides a holistic caching mechanism for iterative data processing workloads. I'm Wook Song, and this is a work that I've been done while I was finishing my PhD from Seoul National University. I'm currently working at a company building an efficient serving system for generative AI. This is a joint work by researchers from Seoul National University, Friendly AI, Samsung Research, and UNIST. To give you a brief context, for running graph processing or iterative machine learning applications on distributed data processing systems like Spark, caching plays a critical role as a particular model that each algorithm tries to develop with such applications are repeatedly reused among the different iterations. In order to efficiently reuse these intermediate data, existing data processing systems provide APIs in the Dataflow SDKs to enable users to annotate the datasets to cache within their applications. These data are repeatedly cached and unpersisted along the iterations in units of datasets consisted of a set of data partitions scattered among the distributed machines. However, as the future convergence of the model is unknown prior to the actual execution, such caching actions have to be done in a greedy fashion, simply by adhering to the user annotations, unquestioning about its correctness or efficiency. As a result of such existing caching mechanisms, the cache data size inevitably grows constantly with the progress of the iterations as more and more intermediate data build up along the iterations. Also, due to the data skew, the amount of memory usage and evicted data are inconsistent among the different distributed executors, leading to bottleneck executors, which poses greater challenges. A naive solution to handle the growing amount of intermediate data would be to over-provision enough memory, but this often is an unrealistic solution, as reserving memory capacity of more than 10 times the input size is extremely costly, while at the same time it's not a solution that always guarantees enough memory for the upcoming iterations. Therefore, dealing with the constrained memory space for caching is an important and a challenging problem to solve in iterative distributed data processing, also because the memory size is difficult to scale in or scale out. Since the memory space is inevitably constrained, evictions are constantly required within the memory space to evict some existing cache data when trying to cache some new data. Therefore, the main aspect of optimizing intermediate data caches is to reduce the non-trivial recomputation overhead as much as possible while recovering the data in memory upon the future invocations of the datasets within these constrained memory spaces. These computation overheads can become super long if recomputations have to be done from a very old ancestor partition. To overcome such problems, existing systems provide an extra configuration to spill the intermediate data to disk instead of just unpersisting them upon memory evictions so that they could read the data back from the disk instead of recomputing them from the ancestor partitions. But in that case, the optimization should reduce the serialization and deserialization overheads and the disk read-write overheads, which are not negligible with large intermediate data. Moreover, it's not easy to choose one configuration over another since the disk I/O costs can vary among the different applications. In the meanwhile, conventionally, the caching, eviction, and the recovery layers within these distributed data processing systems are separately designed and works independently according to some predefined user annotations and configurations, and are triggered by a certain condition, all working in a agreed manner. We figured out that this fundamental design of these independent layers are the root cause of various limitations. To overcome this situation, instead of thinking caching, eviction, and recovery separately, we aim to provide a unified caching mechanism that can derive a blueprint of the optimal cache state before taking action. We aim to take such actions based on dynamic measurements of system metrics and predictions of the potential costs for the different partitions of intermediate data to automatically manage the constrained memory space on a system level. Let me point out the main differences that come from this design compared to the existing mechanisms. First, instead of blindly adhering to user annotations for caching datasets, our system aims to cache only the target partitions that are to save more of the potential costs in the upcoming invocations. Second, instead of simply following a predefined eviction policy, we aim to evict the partitions that will incur the least potential costs in terms of both the recomputation and disk I/O costs. So the consistent similarity here is that we need to aim to lay out and compare all of the disk I/O costs and the recomputation costs and cache the partitions with the greater potential costs and evict the cheaper ones, which is in our example partition C, since it would be cheaper to recover C than the other partitions. As you can probably guess, keeping track of and estimating these potential costs is a crucial factor in our system design. In fact, this is not an easy task due to the dynamically changing data dependencies. One example case would be that while the recovery occurs upon subsequent accesses of a particular partition, the time to compute a partition can become longer and shorter according to which partition are cached and evicted. Another case would be that the number of cache references also change according to the changing cache states. For example, cache partition B is initially referenced once and C twice in the example shown on the slide, but an eviction of a partition C leads to 3 cache references of partition B. From these cases, we can infer that both the recomputation costs and the future references dynamically change according to the cache status. Therefore, to achieve such goals while meeting the requirements, our system is designed to work on 3 main system components, built upon these design principles. Simply put, we wish to 1. Provide an accurate tracking and estimation of the partition recovery costs, and 2. Make a unified cost optimization function based on these metrics, and 3. Offer automatic caching decisions based on a fast ILP-based solution. This works in 3 steps on our system. First, we initially build a DAG-shaped cost lineage based on an initial profiling run. Then, on the DAG-shaped cost lineage, we record the partition metrics which would perform the estimations for the potential recovery costs. And finally, with the estimated potential recovery costs, we derive the blueprint of the optimal caching decisions, calculated from the results of the ILP. Let's see each step in further detail. First, to build a strong basis for our caching mechanism, we perform workload profiling and dynamic tracking of the metrics with which we can infer the recomputation and disk costs for each partitions, along with the current and future reference counts and the potential recovery costs. So in the initial profiling phase, we build the initial shape of the cost lineage by capturing the RDDs and dependencies based on a profiling run, while dropping duplicate RDDs to fully capture the dependency information throughout the different stages. And we capture the DAG to multiple iterations until its convergence. Next, on the captured lineage, we record the computation time and the partition sizes in the initial iterations, while they do not yet suffer from cache memory shortages. Now, through the information recorded on our cost lineage, we can induce the further iterations and perform regression to infer the data sizes of future partitions. And also, we automatically trigger caching on the partitions with future references upon each stage execution, while also automatically unpersisting the partitions without any future references. In the case for inferring the potential disk and recomputation costs, we perform the estimations based on the recorded metrics as shown on the slide. First, the disk cost can be calculated simply by dividing the size of the partition by the disk throughput. And the recomputation cost can be calculated by recursively adding up the computation costs up to the source data or up to a point where an ancestor partition is cached in memory. Based on these calculated potential costs, we design a decision-making algorithm where it is triggered when we need to evict some data to cache some new data in memory, and also when this action is expected to reduce the total amount of potential recovery costs. In the end, we incorporate this within a unified cost function in the form of an ILP, where we try to reduce the total potential recovery costs for the couple of coming jobs or stages by managing the state and the location of each partition to be either in memory, disk, or unpersisted, while abiding by the memory space constraint to reduce the potential costs and timely optimize our cache storage. Where, as we have mentioned, the recovery costs and disk I/O costs are derived from the profiled partition metrics. Blaze is implemented on top of Spark 3 with around 6,000 lines of Scala code and is activated with a bash script that can be executed asynchronously to the data processing pipeline. For deriving the caching decision, we use the Groby Optimizer version 10, a state-of-the-art ILP solver. Next, to our evaluations. We have used 10 executor nodes with a single additional master node with the specifications shown on the slide. Our evaluations are done on 6 different applications whose peak cache size grows up to 170 gigabytes, with the details thoroughly described on our paper. Let's start with an end-to-end job completion times on the different applications with different baselines. The 2 sparks correspond to the conventional Spark with the memory only and memory and disk configurations. Spark plus Alluxio uses Alluxio, which is a tiered distributed storage for optimizing the management of cache data with serialization support for compression. LRC and MRD correspond to least reference count and most reference distance, which provide a more sophisticated eviction policy than the conventional LRU. And finally, Blaze is our system. You can see the performance benefits on the slide and the detailed descriptions on the paper. It achieves up to 2.86 times speedup compared to memory and disk Spark, and up to 2.52 times speedup compared to the memory-only Spark. Let's check out the task execution time for the recomputation overhead and the disk I/O overhead. One thing I would like to highlight here is that while the default Spark uses up to 70% of the execution time on disk I/O overheads, we can see that Blaze reduces the disk I/O overhead by 95% on average by using the constrained memory space in a more effective and efficient manner, and thus by incurring less evictions overall. Finally, we've also done an analysis comparing the effect of the individual components that we built on top of Spark to build Blaze. First would be the automatic caching and persistence of partitions without the future references. And second, we include the cost awareness while selecting the victim partitions. And lastly, we include the ILP-based cost optimization solution in our automatic caching decisions. Here we can see the individual effects of each of the components in Blaze, and we can see that each component plays a critical role in Blaze's performance. In a nutshell, Blaze overcomes the fundamentally inefficient caching mechanisms in iterative data processing workloads by providing a unified caching mechanism based on the profile metrics and sophisticated estimation of the potential recovery costs to derive the best state of each partitions through a cost-optimizing ILP. Thank you for listening, and that's it for today's presentation. Have a good day.